Hey guys, and welcome back to this class, Unsupervised Deep Learning in Python. In this lecture, we're going to talk about PCA, or Principal Components Analysis. There are two components to their description. First is describing what PCA does and how it is used, and then the second is the math behind PCA. So what does PCA do? Firstly, it is a linear transformation. If you think about what happens when you multiply a vector by a scalar, you'll see that it never changes direction. It only becomes a vector of different length. Of course, you could multiply it by -1 and it would face the opposite direction, but it can't be rotated arbitrarily. If you multiply a vector by a matrix, it can change direction and be rotated arbitrarily. So that is what PCA does. It takes an input data matrix X, which is n by d, multiplies it by transformation matrix Q, which is d by d, and then you get back some transform data Z, which is also n by d. If you want to transform an individual vector X to a corresponding individual vector Z, that would be Z equals QX. It's in a different order because when X is in a data matrix, it is a 1 by d row vector, but when we talk about individual vectors, they are d by 1 column vectors. What makes PCA interesting is how it chooses the Q matrix. Notice that because this is unsupervised learning, we have an X but no Y, or no targets. Another view of what happens when you multiply by a matrix is not that you are rotating the vectors, but you instead are rotating the coordinate system in which the vectors live. Which view we will take will depend on the problem we are trying to solve. One use of PCA is dimensionality reduction. When you're looking at the MNIST dataset, which is 28 by 28 images, or vectors of size 784, that's a lot of dimensions and it's definitely not something you can visualize. Note that 28 by 28 is a very tiny image, and most images these days are much larger than that. So we either need to have the resources to handle data that can have millions of dimensions, or we could reduce the data dimensionality using techniques like PCA. We of course can't just take arbitrary dimensions from X. We want to reduce the data size, but at the same time capture as much information as possible. So if we want to go from 784 to 2 dimensions so that we can visualize it, we want those 2 dimensions to have as much information from X as possible. How do we measure this information? In traditional PCA and many other traditional statistical methods, we use variance. If something varies more, it carries more information. You can imagine the opposite situation, where a variable is completely deterministic, as in it has no variance. Then measuring this variable would not give us any new information because we already knew what it was going to be. So when we get our transform data Z, what we want is for the first column to have the most information, the second column to have the second most information, and so on. So when we take the 2 columns with the most information, that would mean taking the first 2 columns of Z. Another thing PCA does is decorrelation. You can imagine that correlations mean some of the data is redundant because we can predict one column from another column, for instance using linear regression. So now if you take the coordinate system rotation view, you can imagine that if we rotated our coordinate system to be aligned with the spread of these points, then the data would become uncorrelated. So again, the question is, how do we find Q so that we rotate the data in exactly this way? Once we have the information of our data sorted in descending order in each dimension, we can just take the top 2 and make a scatter plot. This will then give us an idea of the separation of the data points, and it allows us to create a visual representation of high-dimensional data. The last application of PCA we'll talk about is preprocessing and overfitting. You can imagine that our data is often noisy. Hopefully the noise is small compared to the true pattern. In that case, the variance of the noise, which should be small, would go into the last columns of our transform data Z, at which point we could just discard it. We could then feed this new data into a supervised machine learning model such as logistic regression. In fact, we did this in my previous course. So by getting rid of the noise, we are preventing overfitting by making sure we are not fitting to the noise. You'll see that this idea of unsupervised pre-training will come into play again when we study autoencoders and RBMs. Yet another view of PCA is that the transform variables Z are the latent variables, as in they are some sort of underlying cause of the data X. Then it makes sense that they should be uncorrelated because they are just independent hidden causes. It also makes sense that some of the data in X is correlated because they are just measurements you're taking of some data that is produced by a combination of those hidden causes. What we are assuming when we do PCA is that the data is a linear combination of those hidden causes. In fact, with PCA, the linearity goes both ways. The latent variable Z is a linear combination of the observed variable X, but if you were to do a reverse transformation, the observed data X is also a linear combination of the latent variable Z. You'll recall that we first encountered the idea of latent variables in my unsupervised learning course on clustering and Gaussian mixture models, because those models assume that the identities of the clusters were the latent variable.